Hello everyone. Today we are going to discuss on the topic of chip designing. I am from Object Automation System Solution. So we are going to teach you with a joint program with NAELT Calicut. So let us see how this chip design is from code to silicon. So let's start with a simple idea. First, the race for compute is where the race for the future, and thus the heart of the computes are the chip. So if you see the world shift, we are living through a massive technological shift driven by three powerful forces. That is artificial intelligence, sovereign compute, and edge intelligence. If you come across the AI is no longer an experimental; it's everywhere, from chatbots to drug discovery to financial systems. But AI run on compute and compute runs on a silicon. The more advanced the AI, the more specialized the chips it requires. So now the nations and the organizations are realizing that relying on an external chip supply is risky. To control over the compute is becoming a matter of national security and economic independence. So companies now want to design and build their own chips. Like the computation is moving closest to where the data is generated. So in devices, cars, medical equipments, instead of sending everything to the cloud, the decisions are made in a real time at the edge, and that demands the purpose build efficient chips. So this isn't just a tech trend; it is a global shifter in how the world compute. If you see the chips, which is going to control the future. So the chips are not just components; they are control units for entire industry. Like in data centers, where the custom silicon drives massive efficiency gains and determines who leads in the AI infrastructure. And in healthcare, it just like its AI chips enables the real-time diagnosis and medical imaging at a point of a care. Like if you come in the defense, the sovereign compute ensures independence and security for foreign supply chains. In automotive, the autonomous systems relies on the chip that can make split-second life critical decisions. So whoever designed the chips are going to controls the performance, cost, securities, and innovations. The and like now, if you come across our positioning, we do stands in this transformation. So we are entering at exactly the right moment and with the right approach. That is open power plus open hardware evolution. Instead of closed proprietary systems controlled by few players, we are moving into towards an open ecosystem where open architecture that allows the innovations at every level and customization for specific workloads and industries. So the faster development cycles and broader the collaboration. This is a shift similar to what the open source software did for computing decades ago, and now it's happening in the hardware too. So, but why now? Why at this moment? Because all the forces are relying aligning demands for the compute is exploding and AI is pushing the hardware limit. Nation wants control, industry needs specialization, and open hardware is unlocking the new possibilities. The combination doesn't happen often. So this is not just an evolution. This is once in a generation inflection point. So the chips are no longer just a technology. So those who design the chips are going to design the future. And now let's discuss about the big architecture. That is, uh, we have talked about why the chip matter. Now we'll see how the actual chip works. So let's see from start. Like, what is a processor? So at the core of every compute system is a processor, but that can mean for few different things. First, the CPU. This is the brain of a system. It handles, controls decision making and general purpose computation. Second, the SoC or the system on chip. This integrates multiple components like CPU, GPU, memory, and all on a single chip. Think of it like an entire computer compressed into one piece of silicon. Third, accelerators. These are specialized units designed for specific workloads, like especially for the AI and machine learning, so they can handle a massive parallel computation, such more efficiently than a CPU. So the modern systems are not just one processor; they are the combinations of CPUs and SoCs and accelerators working together. And we have a planes of operations. Now, how does work control to the system is like we can break them into three planes. That is control plane, the data plane, and AI plane. So if you see the control plane, this is where the decision makes. It handles its scheduling and OS level control. So what should run and when. And in the data plane, like it is like a mover. It handles high speed data transfer, moving the data between the memory, storage, and compute units. So this will like tell how the data gets and where it need to go. And if you see in the AI plane, this is just the executor for the intelligence. It runs tensor operations, influence, and model execution. Think how we actually compute the AI workload efficiently. Um, Together, these three planes ensures the system is controlled, fed with data, and able to compute intelligently. And we have the layered architecture stack. If you come across, like you can see application, there is the top layer, that is what users interact with, like web apps, AI models, analytics, edge services. So this is where the values is created. And operating systems like Linux, the OS sits below the applications and manages everything, like scheduling the task, managing the memory, and handling the security, and controlling the hardware through drivers. So it acts as the bridge between the software and the hardware. The runtime layer, this is where the workloads are optimized for executions. That is HPC runtime, a framework like PyTorch or TensorFlow, and libraries like MPI. And we have the GPU accelerator interface like CUDA. So this layers ensures the software runs efficiently on the hardware. Hardware, that is the main foundation. At the bottom, we have the actual silicon. That is CPU, FPGA fabric, AI accelerators, and memory interconnect. This is where the computation physically happens. Now let's see where the open power going to fit. Right at the foundation in the hardware layer, the open power defines the CPU architecture and immigrates with accelerators, memory systems, and high-speed interconnects. But more importantly, it's an open that is not controlled by a single vendor, auditable, that is transparent and secure and sovereign, that is anyone can build and customize it locally. So each layers builds on one below it. Application depends on the OS, and the OS depends on the runtime and the hardware, and everything ultimately depends on the chip. So if you control the bottom layer, you influence everything above it. So we are not just talking about the hardware. We are talking about the foundation of the entire computing stack, and which platform like open power, we are making the foundation open, customizable, and future ready. Now we can see the AI stack is splitting. Let me just tell you, like we are seeing a structural shift in the global AI ecosystem. The AI stack is no longer an unified; it is splitting into multiple parts. Like if you see that we have three stacks. That is first the US lid stack. This is what most of us were familiar with. It is built around NVIDIA hardware, cloud platforms like AWS, Azure, and Google Cloud. So the flow looks like hardware to cloud to developers. And the model is powerful, but is also centralized. You depends on cloud providers, proprietary hardware, vendor control ecosystems. And the second is like the China led stack. China is building its own independent ecosystem. Here we see the Y and chips, the AI models like DeepSeek, and the focus is self-reliance and national control. The stack is highly integrated, locally controlled, designed for domestic ecosystem. And the third is like open power led stack. Now this is where the things going to get interesting. This is not controlled by one country and not controlled by one company. This is an ecosystem built on open power processor, open hardware, and open ISA. That is instruction set architecture, and the flow looks different. Hardware to sovereign infrastructure to open innovation. Instead of locked in, it enables freedoms and flexibility. Why this open power matter is first the open ISA. That is no vendor locked in. You are not dependent on NVIDIA, ARM, or Intel. You can design, modify, and control your own processor. Second, it is sovereign deployment. That is, companies and enterprises can build their own infrastructure, their own data centers, their own AI systems. Full control over data and compute. The third is like full stack ownership. That is from RTL to FPGA to the silicon. You can control everything, not just a software, but the entire hardware stack. Fourth is like the innovation engine. The ecosystem is ideal. University, startups, researchers, because there are no license barriers, uh, the innovation becomes faster and distributed. Then we have the custom AI accelerator. Instead of generic hardware, you can build a domain-specific chip optimized for healthcare, defense, automotive, edge AI, and so we are moving from the world of one dominant AI ecosystem to the world of multiple AI ecosystem, a multipolar AI future. And in this future, the open power represents something very important, a neural open alternative, sovereign alternative. So now it is not controlled by any corporations or not limited by geography, but accessible to anyone who wants to build. So the open power enables sovereign intelligence for the world. Now we'll see about the open power and microwatt. Let's move from theory to something real. So what I'm going to show you now is a fully open processor ecosystem, a real chip that you can study, modify, and run the Linux on. This is the open power plus microwatt, like where the open power is come across like first, what is open power? Open power foundation was created in 2013 by companies like IBM. The goal was simple, open up the processor architecture. Traditionally, the processor architecture like ARM and x86 are closed. You need license, you need fully visibility, and you depends on the vendor. Open Power changes that. It provides a royalty-free instruction set architecture, full public specifications, and freedom to build your own processor. So instead of being logged into a vendor ecosystem, you can run your own silicon. The open ISA and versus proprietary. That is, in the open ISA like power, the fully specialized specialization is public, no license fee, no NDS. So anyone can build and extend it. That means it has the transparency, flexibility, and independence. Now, if you compare to the proprietary architecture like ARM or x86, you need to pay for access. Specs are restricted. Vendors controls the roadmap. You cannot fully inspect or modify the design, and most importantly, you depends on external supply chains. So the key idea is whoever controls the ISA controls the computing, and the open power gives that control back to you. Um, okay, now we have seen what is open power foundation. Now let's see what is microwatt is about. The microwatt is a open source implementation of Power ISA, that is instruction set architecture. It is a CPU designed returned in VSTL. So this is not just a model or simulation. This is actual processor design that you can read, modify, synthesize, and runs on a hardware. What makes this microwatt powerful is it implements the Power ISA 3.0 architecture. It is simple, readable by the design, and it is designed for learning and experimentation. And more importantly, it can boot a Linux. So let me repeat that. That is, it is an open CPU. It is written in VSTL and that can run a full operating system. And let us quickly look inside the what is inside a microwatt. The microwatt is designed to be simple. That is, it has 64-bit architecture. It has 32 registers, and it works on a five pipeline stage like fetch, decode, execute, memory, write back, and it is an in-order execution. So it also includes some basic catch support, an optional MMU, and it is simple branch handling. So the idea here is not maximum performance, but the goal is clarity, audibility, and portability. So you can actually understand how the processor works. Now, like if you see what is this like real or just academic? This is real. The microwatt can boot the Linux kernel and run the processor at the OS and use the open SPI firmware. Uh, and it can compile with GCC, runs on FPGA platforms. So from VSTL code to FPGA to running a Linux OS, everything is open. Like why it is matter is like you can remove the sovereign dependency, you can audit everything, you can control your compute stack, and you can customize the silicon. You can here with the help of microwatt, like you can extend the ISA, your instruction set architecture, and add a accelerators and build your own chip and go from FPGA to ASIC. So it's helpful like university innovations, like where now the students can learn the real CPU design, and researchers can experiment it freely, no license barriers. So finally, the microwatt and the open power and microwatt can prove that the open silicon is real, not just an idea, not just a research, but a fully working system. So if you control the processor, you can control the entire computing stack. So that's control is now accessible to everyone. Now, like I want to show you something very important. Till now, like we have talked about chip design, open power, and microwatt. But this is where the everything becomes real. We are not just designing and processor. We are actually running A on it. Uh, So what's running the microwatt CPU runs on a fully Linux operating system. This is not simulation. This is not theory. This is the real system booting Linux on hardware. So once the Linux is up, it behaves like a normal system. You have a terminal access, file system, and program running. Now the interesting part starts is like I just show you here in the terminal, like how we are going to boot a Linux. Already we had flashed the microwatt bit file and the ELF file. That is, here we have the code that has been available in the GitHub for the microwatt. Just you can get the code and you can convert the code, RTL code into the bit file so that we can able to flash it to the respective FPGA. So we have a board called Arctic A700T FPGA board that what we are using. Like you can use the different types of board, for like what you have. Then we have to convert the your RTL code based on the board that you have to the bit file. Then we have to flash the bit file to the board. Then the FPGA board will now act as the processor, the CPU processor, what right now we have flashed. So right now with this in the processor, we are going to boot a Linux into this. This microwatt is capable of booting a Linux, so that we are going to create a specialized image that is going Linux image that is run for the specialized architecture, like for the microwatt for the processor. And after booting, like you can see how it look like. Yeah. So this is our server, which is the Silicon server, where we have a board, FPGA board, uh, which is being connected to the server, and then we can access it from anywhere. Like I just already had coded I just already flashed the microwatt code. What we have to do is we have a tool like Vivado, which will convert your actual code, your RTL code, into the bit file. So the bit file is nothing but which contains the zeros and information, zeros and one like information for permission to understand. So to flash to program the FPGA board, we need our code to be converted into the bit file. So using the tool like Vado or like anything, like we just convert our RTL code into the bit file, and then after we successfully generated the bit file, we just now flashed it into the respective FPGA board like what we have. So where we use FPGA board like RTK 700T, like what we currently use. And then after flashing this the microwatt, now we have seen the microwatt is a CPU processor. Now after we flash it into the FPGA board, the board will now act as a CPU processor. So how we can test it, the processor, like for that we need an OS to run a program like what we are going to develop, like sovereign type of AI systems. So we need a OS that need to be done run inside this processor. So for that, like we are going to boot a Linux into this microwatt. So like how we have a Linux image been there in the online, like we are going to create a specified Linux image specifically, which is going to work for this microwatt architecture. That like I just already been developed a Linux image, and that image also had flashed it into this FPGA board. Right now, in that FPGA board, it has already a CPU processor has been running, and the Linux has been booted. So to open the console, we are just going to run this command. So this will help you. This USB port that shows that where the FPGA board is been connected. So it's where the Linux in the processor has been running with the booted Linux. Let me just run it, that you can see the final Linux console there. Yeah. So let me just yeah. It shows us like the Linux microwatt which has been successfully booted. Like you can see the output. Now like we have log into this microwatt. So like you can now see the detail of this. So the port is like USB 1, and then we just fix the baud rate. So we can see the welcome to the microwatt. Then it has so like the final booted Linux. So now inside this Linux, like you can operate, like you can run your own Linux program based programs inside this. So what now we are just seeing is like we are just running the processor like inside our microwatt processor, which has been available in this open sourcely. With that, we just built a bit file and then flash it into the FPGA board, and then we then put Linux into this, and then we are using that Linux. So here using this Linux, like you can go. So right now, which has been fully available in this open source, like anyone can try to build and then run and your own Linux based OS into the microwatt. Yeah, I had shown you how the booted Linux will look like and how you can start working in that Linux environment. Now we are now going to enter into the AA. We connect this where you can now in the Linux you can run a AA program also. For that, right now, just we have connect the system to the server and run an AI inference through it. So what's happening now is the microwatt system sends the data and the server runs the AI module and we get the output back to our system. So efficiently, we are running AI inside the Linux environment powered by our own chip. And you can actually see the output, prediction, result, processed data. So this is not just a CPU. This is an AI capable system running on open hardware. So, like if you see now, it's matter because it proves something very powerful from an open CPU design. We can go all the way out to booting the Linux, running applications, and add and executing AI workloads. So we are not depends on an external proprietary systems. We are building our own compute platforms from scratch, and this is just the beginning. Right now, we are running AI through inference, but the next step is bring AI directly on the chip. So we can add a AI accelerator, extend the power ISA, and build custom inference engines. So instead of depending on external GPUs, we can design our own chips. And right now, I'll just show you how this AI is running inside the Linux. And once we do that, the possibilities are huge. We can build chips for healthcare devices, autonomous system, edge AI applications, secure governance systems, and custom builds for specific use cases. Final, this is the first step towards building our own AI-powered silicon, and that's where the real impact begins. So, if you want, can make our own AI-powered silicon with the help of this. Then now we can let's move into the core for the entire talk. Like till now, we spoke about why the chip matters and we saw what architecture look like. But now the real question is, how do we actually build a chip? Not just a theory, but step by step from the scratch we are going to see. What I'm going to explain is a complete pipeline. Something as simple as specification, like all the way to the physical silicon chip. And the most important thing to remember here is The entire process can now be done in the open. Uh, like s- Step one. So we just start with the very first step, ISA, Instruction Set Architecture. Now, ISA is basically the contract between the software and the hardware. It defines things like what instruction exists and how the register behaves and how memory is assessed, how program interact with the processor. You can think of ISA as the language that the processor understands. In our case, we are using Power ISA 3.0. So what it makes is important is it is open, it is public available, and no license required. So at this stage, we are not building anything special. We are just building answering one question: what the processor should do. And the next step is RTL. So once we know what to build, we move to the next step where we design the RTL, that is register transfer level, where now this is where the things starts become a chip. So we take the ISA, any one instruction set, and we start writing actual hardware logic. This is done using VSTL or Verilog with any one hardware descriptive languages. Uh, and In our case, like we are going to use the microwatt as your RTL code. So here we define everything, how the instructions are fetched, uh, how they are decoded, and how execution happens, and how the data moves between the register. So if the ISA is the language, RTL is the implementation of that language. At this point, like we can now have a complete processor written as a code. We have some important file inside the microwatt, that is decode file, which is the instruction decode, and execution file, which performs the ALU and branch, that is whether it finds where the actual execution happens after it decodes, like what type of instruction it is, like whether it is an add or subtract or anything, that will be happen in the execute PSTL file. And we have the low store file, that is memory optional, and then code.vstl file, that is the main top level integration file. Then after the step, like next is simulation. This is very important. Like we need to test everything. This is like important for simulation verification. Here we run our RTL code inside a software tools like GSTL, CocoDB, or Verilator. They are all open sourced. And now what we are checking is like whether the instruction is behaving correctly, whether the pipeline stages are working, whether the memory access is correct, whether the system can boot properly. Because here is the reality: if you make a mistake in the silicon, it is extremely expensive to okay. So this like debugging the processor before it physically exists is the better way that we can reduce the expenses. And we run hundreds of tests here again and again until we are confident. So as I said, the simulation step is important. As we see the GSTL, which is an open source VSTL simulator, the CocoDB, which is Python-based test bench framework. These are all some simulation tools. And to check the final waveform, like that we can use the GTK wave. And the next is the FPGA prototyping. After we verified our code that has been running successfully, so for everything was in the software level. Now we have to move into the real hardware where the FPGA stands. That is, you all know FPGA, feed gate programmable array. These are the chips that we can configure. So we take our RTL and load it into the FPGA board. Now suddenly our processor is running on a real hardware. So at this stage, we validate things like real clock timing, input output behavior, memory interactions, and most importantly, we can boot the Linux. And when Linux boots successfully, that's a huge milestone because now we know the design actually works in the real world. Uh, after we just flashed it. So these are some of the support boards like we can perform the code like RTK7 that right now we are using. And then once we just get the bit file and then like we just flashed it into the FPGA board, like we can test it with the real hardware, how it works. Now let's see the physical design. This is also an important thing in the, this is like in the back end part where we actually design the chip. Till now we are just working the hardware and then we just tested with the FPGA board. Here we are going to design a chip from the start, like from the size of a chip to the final layout. So we will get a final GDS2 layout. That is what we are going to send it to the factory for the fabrication. This is also one of the important thing. Let me cover it quickly. So now we know what a physical design. So this is where we convert our RTL code into the actual chip layout. Using tools like open source tool like OpenRoad, we go through multiple steps. Let me walk you through them one by one. The first step is synthesis. We convert the RTL into the logical gates in the synthesis stage. And then the second is the floor planning stage. We decide where the things goes on. That is, in the floor planning stage, we design the size of a chip and place your macros into it, and then we place the IO pins around the core area. Then then comes the placement stage, where we place all the components physically. So inside a design, we have several types of logic gates. As you know, the all the logic gates that we call here as the standard cells were going to get placed in this placement stage. There will be some millions of standard cells will be there in the design. So that we have three types in the placement stage. That is a global placement, detailed placement, and the legalization. So with this, we just make sure that we ensure that all the cells has been placed at the respective area without any overlaps. Then after we place the cells, the next is like the clock tree synthesis stage. This is also an important stage where we make sure that the clock signal reaches everywhere properly. That we just reduce the skew. That is all the flip flops gets the data at an equal time. So the main motive here in the clock tree synthesis is like we have to reduce the skew, and the final stage is routing stage where we connect everything with wires. Like we have metal layers has been passing through that we are just placing the metal layers, the standard cells, and from the metal layers that to the standard cells, the connections that has been connected to in the routing stage. So we connect everything with wires here, and then verification. That is your design rule check and layout is a schematic verification that we just check if the design is valid for manufacturing, and then we get a final GDS2 export file. This is the final file. You can now have a manufacturable chip design. As you can see here, this is the final GDS2 layout will look like. This is for the microwatt that what we have come across in the CPU. That is like this is how the final layout has been look like. This has been built in the open road with the 130 nanometer. Okay, so this is a interface of the open road, which is open road is nothing but an EDA tool, which is similar to the market tool like Cadence Synopsys. Unlike they are like we have to buy the tools and then use, which is very costly right now. But this open road, which is a fully open source tool, like anyone can download it and then start working with like building your own chip with the help of EDA tool. So this is how this interface of the uh, your open door look like. You can see the metal layers here. So what I had run is the microwatt that what we have seen, the CPU processor. That's what like I had run here. This is the final layout of that microwatt, like what that is what you're viewing. So the in the left hand side you have see the types of metal layers. So in this microwatt, like which is you can see it is of 130 HT, like it is being built on the 130 nanometer size. So this microwatt has contained some five metal layers inside this. So this is how the final chip layout will be look like. So you can this is the layout that you are going to send it to the factory, and they will make a actual chip out of it. So here at the left hand, in the right hand side, like you can see the timing report as we had already discussed in the CTS stage. You will just uh, check for the timing. So after the CTS stage, like after we improve the clock timing, that you can check the timing report here, where you have set up a hold violations if there is any, and then you can see the total required time, the capture clock, the arrival time, and what is the slack we just get. So if there is any timing violations, then we have to fix it after the city stage, or like before the routing. Okay. Uh, yeah. So this is about the back end of like the physical design. Uh, and then let's see the final stage, where the tapo. This is where everything becomes real. So we take the GDS file and send it to the semiconductor foundry, for example, TSMC, Intel, or Skywater. So the foundry then fabricate the chips on silicon wafers, cut and packs it and send it back. After a few weeks, you are literally holding your chip. This is the most, this is the, like your code becomes physically hardware. Um, Now let's step back for a second. Why is this entire pipeline important? So this process requires huge companies and expensive tools and closed ecosystem. But today, the entire pipeline can be done using open tools. This means like no vendor logged in, full transparency, full control, and anyone can learn and build. Then, so from ISA to RTL to stimulation to the FPGA and then to the final silicon, we are seeing something very important. So chip design is becoming accessible. So finally, anyone like who understand this pipeline can build the future of computing. So all right, now let's bring everything together. Till now, we talked about chip design and we talked about AI, but what happening today is something bigger. These two worlds are converging. AI is no longer just a software; it's shaping how chips are designed, and at the same time, chips are being redesigned specifically for AI. So the future is very simple. Chips will be AI designed and AI powered. Let's first look at AI inside the chips. We now have neural processing units, NPUs, like, and these are dedicated engines from like for tensor operations. So which means AI can run directly on the chip without needing the cloud. Then we have inference engines. So this allows the real-time decisions, low latency, and efficient computation. And finally, the FPGA and ASIC accelerators. So this allow us to build custom AI pipelines, domain-specific chips, high performance, and low power system. Um, like now, if you flip the perspective, AI is not just inside chips. AI is also helping design chips. We now have AI assist RTL generation, automated floor planning, AI-driven verification. So instead of manual effort, AI is now accelerating the entire chip design process, and this is where your workflow is fit. So combining the terahertz sensing plus AI and open power, Like now we can, you are not just using the AI, you are building an AI driven hardware system. Let's see some of the real world use cases. Now let's make this real. Where does all this matters actually? Healthcare. Imagine real-time diagnostics running directly on the device, and AI detecting the tumors instantly, wearable sensors monitoring the patient's MRI assistant systems at the edge. So, as the key point, no cloud dependency, patient data stays local. And in autonomous systems, now think about self-driving systems. They require radar, LIDAR, camera fusion, all processed in real time with extremely low latency, less than milliseconds. And here the custom chips and FPGA accelerator makes it possible. Then we have data centers where the AI workloads are exploding. So we need custom accelerators, efficient compute, optimized architectures. So the open power enables specialized chips for AI workloads and now the sovereign infrastructure. This is the biggest impact. Countries want to control over compute, no foreign dependency, secure auditability systems, and open silicon enables exactly that, from university to fabrication to deployment. So across all domain, the pattern is same: open power and AI that is going to be control and innovation. So let's see some of the career paths and opportunities here. So where do we fit all this? Like the fields opens a multiple career path here. The first is RTL engineer, where you design the processor. You worked on microwatt, pipeline logic, and verification. Second, like physical design engineer, like you take the RTL and convert it into the real silicon. Like you works on synthesis, floor planning, placement, and routing. And the third is FPGA engineer. You bring designs to life on hardware. You handle bit streams, timings, and hardware debugging. The fourth is a hardware engineer. This is the future. You combine AI, compilers, hardware design, building next gen accelerators. And beyond the rules, they are real opportunity. Industry internships, global collaborations, open power ecosystem, research publications, and the most existing part is you can tape out a real chip during your learning journey. This is not just theoretical learning. This is hands-on silicon experience. And one important thing is there is a massive shortage of chip designer. So this is not just interesting; it's a high impactful career path. Now let's see with the our closing vision. So now let's end up with the vision. 100 chips from university. Think about what this means. Students not just learning theory, but actually building a real processor, holding a silicon that they are designed. So this vision is to build on three ideas. That is open ecosystem, collaboration across the university, industry, and global community. Build your first chip from RTL to FPGA to silicon in one journey, and then it's sovereign AI for future. So we design the systems that are independent, secure, locally controlled, and this is especially important for countries like India. We don't need software engineers; we need a chip designers. So this is not just a course, not just a project. This is a movement. So if I have to leave you with this thought, don't just use AI, build the AI hardware that powers it.